Good afternoon, good morning, good evening, everybody. Thank you for joining us again this Friday for our next talk in the series of IEEE Rio Grande do Sul CASS Talk. So today we have the pleasure to have here Professor Ricardo Jacobi from University of Brasilia. And I also like to thank Professor Luciano Agostini from Federal University of Pelotas to be the chair of this session.
Again, I am Luciano Agostini from Federal University of Pelotas. I'm very glad to be here today with my friend, Professor Ricardo Jacobi. This is a very important and interesting research topic, and we are excited to learn with Professor Jacobi about this topic. Professor Jacobi holds an BS-EE and MSc-CS degrees from Federal University of Rio Grande do Sul in 1982 and in 1986. He received his PhD in Applied Science Microelectronics at the Université Catholique de Louvain, UCL, Belgium in 1993. He's currently a professor at the Computer Science Department of University of Brasilia. He was director of the Institute of Exact Science from 2004 to 2008, and the vice president of the UnB Gama Campus from 2008 to 2012. Professor Jacobi founded the IEEE CASS Chapter at the Centro-Norte Section in 2011, and was the chapter chair from 2011 to 2014. Section chair from 2015 to 2019, and Brazil Council chair in 2018-2019. His research interests are in computer systems architectures, digital design, custom architectures for hardware accelerations, and EDA. Thank you very much, Jacobi, to be here with us today, and please go ahead. The word is yours.
Thank you very much, Luciano, for your introduction. I thank you and Ricardo also for this kind invitation. I'm very happy to be here among friends. So I have a lot of slides here. I will try to go fast because we have not so much time. But so the topic we are going to talk about today is algorithms and architectures for morphological image processing. And so we are going through this agenda introduction. I will talk a bit more than morphological reconstruction, which is our main topic. I will cover some introduction of some basic operations in morphological processing, discuss algorithms and architecture, talk about some experiments we have done, and then finally with some comments. So we start working this area because we have a colleague in University of Brasilia that was cooperating with some people in the United States, where they were working on medical image processing. More specifically, they were trying to identify cancer cells in brain slide images. So the brain slide images, they are very high resolution images, and in their workflow, they use a lot of image processing operations. And some of those operations are based on morphological reconstruction algorithm, which is very time-consuming. And then, so this guy George was working with the speed up of those algorithms in many cores and GPU platforms. And then we start working with FPGAs to see what we could do in this area. So mathematical morphology, morpho is related to shape. So it's the manipulation of images based on their shape. It has a lot of applications. So for instance, we can use for boundary extraction, skeleton, we'll try to find a skeleton of a shape. Convex hull, morphological filtering, image segmentation, so it has a lot of applications. It's based on set theory, especially for binary images, and lattice theory for the extension to gray and color images. So talking about binary images is very easy to understand the principle. So we can think about a binary image has a set of, the onset will be the pixels on the foreground, and the offset will be the pixel on the background. And that could be thought as a logical function too. So we have the onset of the function and the offset of the function. So in this case, Operations like AND between two, logical AND between two images is equivalent to the intersection between the sets. In this case, the sets of pixels of the front end of the image. And also the order, logical operational OR could be compared to the union of the sets. And those operations, morphological operations, usually relies on the use of a structuring element. In the structuring element, here we can see two of them. They are a pattern, a shape that defines which pixels are going to be used to compute a new value for the pixel in the origin. So the most common shape window we use to represent those shapes is a square, but it can have any shape, in fact. So in this example, we have in the left square here, we have defined the 4 pixels, the 4 neighbors of the center point that will be used in compute a new value to this central pixel, and on the right side we have 8 connected components, which means that all the pixels in the boundary will be processed in to compute to update the image. The origin here is indicated in the center of the square, but it could be any point, in fact. Okay. And as the image resolution goes higher and higher, we need to, sometimes we need to have higher, we need to have larger structuring elements. So here an example, we can 3 by 3 is we have a small element, but we can have 5 by 5, 9 by 9, and so on. So if you increase the size of the structuring element, so you have thicker lines on the operations. And as usual, those structuring elements are scanned for the image. So from the pattern is displaced over the pixels one by one, usually in the raster scan wave from the upper left to the bottom right pixel of the image. The most common operations are, the most basic one are erosion and dilation. Combining erosion and dilation, we can easily build opening and closing operations, and then we have more complex operation has hit or miss, skeleton, and morphological reconstruction. Here is the illustration what would be a dilation, for instance. So this is a binary image, so we have 1 and 0s. We can think about logical operations too. So we scan the image, the original image is that in red. We scan the image with our structuring element, and then the resulting pixel in the middle that will be updated, that's indicated in this case, will be 1 if the structural element intersects the onset of the function. You can see here, I don't know if you can show here, so this pixel intersects this pixel, so the operation we do is an AND between the pixels and the elements of the structuring element, and then we do an OR with them. So in this case, if you have, basically if you have 1 pixel of the onset inside the structural element, the resulting new pixel will be 1, 2. So if we scan the image with this structural element, what happens is that we enlarge the frontier of the image, like is shown here in gray. So the original image here is in orange or red, and the new boundary is that in gray. That means the image was enlarged or dilated. The other operation, the complement, will be the erosion. Erosion follows the same principle, but the idea is that we'll remove pictures from the boundaries of the shape, and also if you have some holes inside, it will enlarge the holes. So the only points that remain when we pass this structuring element are those where all the points in the image are 1s too. So if 1 point of the offset, if there is a 1, 0 intersecting the structuring element, then the new pixel will be 0, 2. So from this image, only those pixels will remain. Opening and closing are combinations, direct combinations of dilation and erosion. Opening is erosion followed by dilation. So here is an example where we have 2 letters, J here on the left. You have J with a lot of noise here, small dots, white dots that are noise. If you do an opening, what you do is first an erosion, and depending on the size of the structural element, all those dots will disappear, and the boundary of the J will be reduced. But then you apply a dilation with the same structural element, and you restore the original image. The main image is stored, but the noise is suppressed. So it works like a filter. Closing is another operation to the complement. So here we have the noise inside the image. So there's black dots here, so our noise inside this J. When you do a dilation over this image, we are going to increase the boundary. The J will become thicker, and all the black dots inside the J will disappear. Then it follows by erosion with the same structural element, and you recover the original image without those noise inside. So it's two kinds of filtering effect. The morphological reconstruction is a bit more complex. So it's defined here for binary images. So we have two images, in fact, must be used to compute the morphological reconstruction. In the binary case, we have those images here. We have the gray shapes here defines the mask image with the F function. And the J image is what we call the marker function. Marker is contained in the mask. And the idea is that the image, in fact, is composed by a set of regions of connected pixels. So this shapes like a region of connected pixels. And what the J image, which is the marker, do is to select which regions will be part of the resulting image. So here we have marked these three shapes, and these three shapes after reconstruction appears and the others disappear. So markers like marking which elements will be part of the final image. This can be computed by dilation. If you take the marker image here, the black region here, and start dilating his boundaries, but restricted to the onset of the mask, so we cannot go into the offset of the mask, we can recover or rebuild or reconstruct this connected region for the mask image. So the mask image will have some elements selected by the marker image. When we extend that to gray level images, so one way to formally describe that is thinking about, so the gray level, here we have an example with one-dimensional images. So we have the axis, one-dimensional axis here, and the intensity of the image displayed here. If you're thinking formally, we can think that each level of the intensity could be thought as a binary image. So this image here could be think about a pile of several binary images stacked one after the other. And then we can work with dilation and erosion the same way. So here in this example, J here is the red line here, the red function, red image. And then this is the marked image. The blue one, this is the eye is the mask image, and the green one, image here is the reconstruction of the mask with the marker. So in this case, you see that we have the dilation. So the J image is dilated to the sides, to the left and to the right, but limited by the mask. In the same way on the binary case, but here in several levels. So here you see the direction of, so in this case, we are going to propagate the value of those pixels up to arrive to the blue image that limits the expansion of the marker, the J. So this have the effect of making more, more thicker lines, so the image gets more clear. It can be thought as one intuitive way to think about this is like a flooding. You have some valleys and mountains here, and you start putting water inside, and you are flooding them, but with a limit defined by the mask image, the blue one here. So here is one example that is provided by Luc Vincent in this paper in '93. So Luc Vincent proposed these main algorithms that are still used today for the manipulation of morphological reconstruction. So one example of how you can use this morphological reconstruction is in the extraction of the microaneurysm. So this is a picture of the retina inside the eye, and you have some microaneurysms that are those small dots in white here. And we have the blood vessels here, which are very thin too. So just filling the gap with the background doesn't, with thresholding this doesn't work, because you could affect the vessels too. So just to extract those aneurysms, what they have done, they have proposed a set of opening operations that change the image into that. See that the vessels are more straight lines like that, but the aneurysms disappeared. Then you use this image has marker and this has mask, and expand, make a reconstruction, and you rebuild the original image but without the aneurysm. When you subtract the original image from this one, you get the points of interest are those. So quite interesting the way they manipulate to get, and it's not trivial to get those points. Well, in terms of algorithms, we have basically four main algorithms: parallel reconstruction, sequential reconstruction, wavefront propagation, which is we call also Q-based, and a combination of both, which is called the fast hybrid reconstructions. When we do parallel implementations, then we must deal with image partitioning, and then we can process the blocks independently to speed up the processing. But we have to do a post-processing step, because we have some artifacts that arise, some discontinuities that arise in the borders of the sub-images. The parallel reconstruction is very simple. It's just to take the pixels in an arbitrary order and then dilate them. So if you keep doing that, so the main equation here, you see the new value of one pixel will be the minimum between the maximum point, between the point of reference, this P, and his neighborhood. Remember the structural elements, so we are computing the maximum. You pick the maximum value of the neighborhood and put in the center, but you cannot go up beyond the mask. So you make you must make a minimum, choose the minimum value between this maximum and the mask. So this is very simple. When we have no more propagation, so updates on pixels, you have finished the process of reconstructing the image, but it's very inefficient. Then another more efficient algorithm was proposed is the sequential reconstruction, where we combine a raster scan, where we displace the structural element in the raster scan wave from top to bottom, and follow it by an anti-raster scan from the bottom to the up. So a full scan will be composed by a raster and an anti-raster scan. And what is interesting is, in this case, the structural element is selected this way. So when you do the raster scan, you only pick the upper and left pixels, including the central one. So we are going to apply that formula. We compute the maximum value of those 5 pixels and limit it by the mask. So we make it the minimum with the value of the mask at this point, and this will be the new value of the central pixel. When you do the anti-raster scan, you process the other pixels on the bottom and on the right. So this way you can see that this movement makes a propagation of the largest value that you compute, because the new value that you compute is kept in the original image. You compute a new value and you write it in the new image, the original image. Then when you displace your structural element, you slide your window, you are using the value you just have calculated here. So that makes a big difference between the basic operations of morphological operations and reconstruction. Because here you have a data dependency that you must update each time. When you have opening or closing, you can process independently easily the partition of the image process independently, because you don't have this propagation feature you can find in the morphological reconstruction. So The algorithm is something like that. So very quickly, just to show, when you do the raster, so you take the reference for each pixel. Remember that this structuring element will be placed all over the image, and for each pixel we are going to compute a new value. So in the raster scan, we compute the new value using those pixels, upper and left, including the center, and on the empty raster, you compute the bottom on the right and the center too. So computing the maximum and then taking the minimum with respect to the mask. If you think that, if you think about a very simple image, we can think that just one scan will solve the problem, but it's not the case. Unfortunately, that's not the case. This approach of sequential reconstruction, in fact, does not work well with rolled up images. That mean spiral cases. You see spiral like that. This is an example based on that paper of Luc Vincent. So you have a spiral, and then this gray is the mask, and this black is the marker. So when you do a raster scan, you have this expansion, then you have an anti-raster, you have this expansion, next another raster, this expansion, and so on. So you may have several iterations until all the propagations are done. So in fact, according to our experience with those images, if you take, for instance, one image of 1024 by 1024 pixels, usually you try to solve that by sequential reconstruction. Usually you are going to several 10, 20 or more iterations until the image is stabilized and you get a reconstruction done. So for that reason, another algorithm was proposed that is based on queues. So it was called queue-based algorithms or irregular wavefront propagation algorithms, because the shape of the expansion will be irregular. And it uses two phases. First, you initialize a queue, but you must scan the image and take the regional maxima. So you put on the queue the maximum points, and then after you initialize the queue, you start taking out elements on the queue. So you pick out one pixel in the front of the queue, and then you look for this neighbor or for the neighborhood of this pixel, and for all the pixels that's smaller than the pixel, the working pixel, you propagate. So this is the contrary of the previous one. In this case, this central pixel propagates to the neighborhood, to its neighborhood. So here you are going to, this pixel will propagate to this 4-1, and each pixel that you change, you put again on the queue, because this can have other neighbors that may be subject of propagation too. So all the processing goes using the queue, inserting elements on the queue, removing elements on the queue too. So this way we have this more or less is the pseudocode of the algorithm here. So you have an initialization phase here, the wavefront propagation where the S is the queue, so we extract one element of the S. You get the neighborhood of this element, put on a queue, and then process all the elements of the queue. And if you have a propagation condition, then you update the value of the neighbor and insert it on the queue to be processed later. So these two algorithms work quite well for different conditions. So the sequential reconstruction is very efficient when you have a large number of pixels propagating. And that's the case when you do the first scan on an image. You should take an image and the mask and the marker. And when you do the first scan, you are going to find a lot of pixels propagating. In this case, the queue-based algorithm doesn't work very well. And the sequential reconstruction is more efficient. But since you may have several iterations, when you, after some iteration, when you have a few pixels propagating, so the sequential reconstruction is very inefficient, because you are going to scan all the image to propagate or update a dozen of pixels. And then in this case, queue-based, it's much more efficient. So take into account this complementary characteristics of those algorithms. So it was proposed a combination of both. So what is called the fast hybrid So the fast hybrid reconstruction. So the idea is that if we do on the first phase a raster scan, a sequential reconstruction, just one scan, a raster and an anti-raster scan, we already may propagate, update a lot of pixels, and during the anti-raster scan, we compute which, we build the queue, we can analyze which pixels can still propagate and put them on a queue. And then after one scan, we stop the raster, the sequential scanning, and start doing the queue propagation. So this combination was called fast hybrid reconstruction. So in the first step, you do one scan, and then on the next step, you apply the queue propagation, the irregular wavefront. In fact, we were curious about that, and then we start to make some experiments. So what I just said is the first case here. Here is one image, and we have here the number of iterations, the number of scans we have done with this image. And here is the processing time. So the first column here is just what is the fast hybrid reconstruction. We do one scan, and all this green column here is the time it takes for the queue-based algorithms finish the reconstruction. And then we thought, well, if you do two scans and then start the queue, so you see here a very significant reduction. If we do three scans and so on, so we continue up to the end here when, in this case, we have the complete reconstruction done by sequential reconstruction, sequentially with 15 scans. So pure sequential here at the end, and here the combination, and you see that they have a convex shape here, where the best result, more or less here, if you do 5 scans, and then we changed for the queue propagation. So we have here a factor of almost 5 of gain with respect to the fast hybrid reconstruction, was the first one. So that was an interesting observation, and then we tried to address that in the works we have done. So we'll talk a bit later about that. So processing larger images, so you see our idea is not to compete with supercomputers, just to use FPGAs to think about embedded applications that could use those algorithms. So, but still, you may have large images, and FPGAs, we know, have a lot of limitations with internal memory, and those algorithms require a lot of buffering and storing images internally, because you must process 2 images at the same time. And then if you want to process the larger image with FPGA, you must figure out some partition or some decomposition technique. So the problem is that when you do a partition in here and try to explain to you, you introduce discontinuity. So think about this small image here. So we have the marker and the mask, and we split in two sub-images. So if we compute separately with 2 processors the reconstruction of both images, you can see here that for P1, processor 1, see that on this border, the largest value of the marker is this one, and the propagation goes like that. On the other side, for P2, you see the largest value is this one for the marker, and the propagation goes like that. So you have here a gap, discontinuity, that can be solved if you process the border. So if you process the border with using the queue propagation, for instance, and then we can rebuild this propagation that was missing. So of course, if you have a large image with a lot of blocks, and you have a lot of those possible discontinuities, and then in the partitioning case, you must reconstruct the sub-image, reconstruct all sub-image, and then solve the borders, post-process the borders to solve these discontinuities. We have done that. So one easy approach is to take an image, for instance, and divide in 16 blocks, and then you can process independently. In this case, it was we were just making experiments with one accelerator, so the hardware accelerator processing based on sequential reconstruction. Remember, sequential reconstruction can be efficient if you have not too much scans to do, and small images have not required not too much scans. And then you may compute all the sub-images, and then you can use, for instance, in the case of a SOC FPGA, where we have the FPGA together with ARM processor in the same die. You can use the processor by software to solve the border problem, do the post-processing. Of course, you may try also to, here is illustrated, if you use for instance, two processors, we can process in parallel the sub-blocks, and then, so we are going to speed up the time to solve all the blocks, to reconstruct all the blocks individually, and then we can have an extra step of post-processing to solve the borders. And one thing that we did too, that is quite interesting, was to analyze if the possibility of having a border overlap. So the idea of border overlap is to allow the image to process some pixels of its neighbor 2. So when we are processing block 2 here, for instance, we not are limited by the original limit of block 2. We can go and process, go into the neighbor blocks. And this, why is the reason to try this? Because maybe with the processing a small overlap, we can solve this small deconstruction for some cases. So that was the idea. So that was an experiment we have done too. In terms of architectures, the most common for sequential reconstruction is the delay line scan, which is very common in image processing. So you have all these elements of, you have some registers here to store the pixels, and each time you read the pixels, the registers are connected with line buffers in a shifter register arrays in such a way that for each new pixel you read, the instruction element moves one bit to the side. So we can process 1 pixel per clock cycle and automatically displace the image, the structure element over the image. It's a very well-known architecture, but it's very efficient for the sequential case. Some works in the literature, there are several works trying to optimize morphological operations, especially coprocessor, that we can do the basic operations, reconstruction with basic operations, and so on. So in this paper here, the guy used the property that a structure element can be decomposed into one vertical vector and horizontal vector. So we can split the matrix in 2 vectors, and the composition of 1D filter with another one, a vertical filter with a horizontal filter, can obtain the same result with much level operations. Think about structuring element with 15 by 15. So you have 225 operations to be done. So if you have 2 filters with just 15 by 15, you go 1 scan with 15 and 1 scan with 15, you can obtain the same result. So that's is what is shown here. So we have the delay line. So you can take the k elements here, for instance, in a vertical filter, and compute the result for each of those pixel in the center when we are displacing this vertical element. And then the results are shifted here, forming the horizontal pixels that are processed by the horizontal structuring elements. So this composition can be very efficient for the basic operations. Other kinds of work is the combinations of morphological blocks in pipeline, like this one. So Tekle Johannes, published in 2018. Here we have several stages, and we have morphological blocks of different sizes. For instance, we have 3 by 3, 5 by 5 here, 7 by 7. And if you make a composition of that, you can have several options of the size of the instruction element. If you apply one after the other, it's similar to applying a larger one. So for the case where we are working on very high density images, very high resolutions, we may have structuring elements very large. So this approach is interesting to be flexible and allow you to choose the size of the structural element that's most suitable for your problem. Well, in our case, we're working on the Cyclone 5, the SOC FPGA with ARM processor and the FPGA. So what we have done here, we have implemented directly the fast hybrid reconstruction that was published in the IEEE Design and Test last year. So you have the raster and anti-raster scan module here, use delay line, as we saw. And then when we stop the sequential reconstruction, we move to the Q propagation, and we finish the processing of Q propagation. So one detail here is that in the ARM, we have training a support vector machine. So support vector machine was trained based on some parameters of obtaining from the reconstruction to try to guess what is the best number of sequential iteration before changing to the Q propagation. So that image I was showing you before, this one. So this one we have training support vector machine to guess and how much iterations I must done before going from the blue to the green here, from the sequential to the Q. And that was trained and was implemented in software and executed by the processor. I will show for you some results later. Using the ARIA 10 board, which is much more powerful, another solution was proposed to use 4 parallel coprocessors. So we can split an image, for instance, 1,000 by 1,000 and 4 images by 500 by 500. And those processors cooperate between them to solve the internal borders of the blocks too. So this we have this speed up of 4 processing units at the same time, and also without need to use an external processor for solving that by software. They solve the internal borders themselves. So that's one approach that obviously achieve a good speed up. So talking about some experiments, the FPGA boards we use are so this one, the DE2, which is the academic one we use in the labs, the SOC kit, where we did some experiments with the partitioning, and the ARIA 10, that is a larger one that allows us to do more complex designs. In the case of DE2, we have just implemented the sequential implementation with the raster and anti-raster, but it's limited by the size of the memories. You can see here, so small memories up to 288 pixels. You see that only 14% of the logic elements were used, but the memory was the problem of that limits the amount of the size of the image we can process. In the SOC kit, we have so in the SOC kit, we have an ARM processor, which has 1 gigabyte memory, and we have also 1 gigabyte memory for the FPGA module. So in this case, we are dividing the image in several blocks, and in our experiments, we use 2 hardware accelerators to reconstruct the sub-images. And then we have two cores inside the ARM, and the 2 cores work simultaneously with the hardware accelerations. And each time we have 2 adjacent blocks computed, so the software started to build to fix the borders here. So that was the best solution. So all the software modules and the hardware acceleration, all of them working concurrently. Of course, we must synchronize. So first, we need to have the blocks, the sub-images processed, reconstructed, and then you can solve the borders. And with this, in this case, we have worked with, make some experiments about the amount of overlap we can use here. So this, the best result we have was for the overlap of 16 pixels. And we have compared it with a pure hardware sequential solution. Of course, we cannot run this because we don't have enough memory to make this solution for the image with 4K by 4K pixels. So we estimated, assuming that we have no memory conflicts, and we can run at the same speed of our FPGA, 150 megahertz. And suppose that we have no memory conflicts and then we can access freely the pixels, so we can compute that the time it will take for a sequential solution in hardware to solve those images. And so the solution using partition and including all the time to exchange images between the processor and the FPGA and so on, and doing and fixing the borders, it gives a gain of around 50%, so twice the speed, half of the time here. Of course, if you try to do it by software on the ARM, we are going to have a large time, so it's not a good solution. Concerning the overlapping of the borders, so we have made some experiment with 0, 16 pixels, 32 pixels, or 48 pixels. So that's the idea. So we have one image block. Of course, not proportional here, but the blocks are much larger. But we have, so we may go 16 pixels in our neighbor, or 32 in our neighbor, or 48. And when the neighbor computes itself, it can go in the same way back in the first one, 16, 32, or 48. And the best solution was 16, and it was quite interesting because the gain is not negligible. We see here the total time, and we could reduce from 6.7 frames for 3.7, or 9.1 to 3.9. So in here, more than twice the speed, just by allowing some overlap between the borders. Notice that the hardware solution will take a bit more time. You can see here, hardware takes a bit more time because we are, if you process the borders, if we are overlapping the borders, invading our neighbors, so we increase the size of the sub-image. Of course, the hardware will take more time to process that. But that saves time in the software phase when we are trying to solve those discontinuities that appears on the border. So it was quite interesting. The gain is really not negligible at all. And 16, so we don't need really to go very deep inside the other. Of course, you always must take into account that those results are for one kind of image, biological image, tissues or human tissues, and this is very common. Medical imaging, you use a lot of morphological algorithms. But of course, if you think about the landscape, then the results could be completely different. Of course, because the propagation, in case the border, for instance, could not, such a small overlap will not save much time if you need to go deeper, very deeper inside the other subblock, your neighbor subblock. In the case of I told you our predictor, our support vector machine, what we have done was that for comparison purposes, we did that. You have this table with the image of 4K by 4K pixels. And then we have some solution, of course, using some algorithms to solve. But what is interesting here is that one, is this data here. So if we have this image, we can compute, for instance, in this case, for this image, with 10 scannings, we can solve the reconstruction of this block. So we can compute the time for each one and determine and find the best solution. So we just compute the time for all of that and say, well, 6 here, 6 iteration plus this small phase of propagation, Q propagation, solve the problem, and it's the best solution. And we computed the best solution, and that's it. And that was called the fast hybrid oracle. Oracle because he knows the best solution. And then we compare with the guessing by the machine learning with support vector machines, and it was quite close. So here, the time for the time difference between the oracle and the support vector machine guessing was quite close, and the guess was better than the other algorithms. So it's quite an interesting thing to investigate more, because of course this work it was training for those a set of images with this problem. So how this scales is a completely open problem. So finishing, finally, About serial reconstruction, so it's very efficient when you have a large number of propagations. So what is interesting in serial reconstruction that we have a very efficient hardware implementation. So you can have this delay lines and you can read 1 pixel per clock cycle. And if you could reach, if you go for silicon, for instance, you have some gigahertz of clock, you can do things really fast. Of course, you need a very good memory hierarchy to have fast access to the pixel, but you can play with the bandwidth you're using to access the image. But this doesn't work quite well if you have a lot of iterations and the number of pixels updates decrease. So you spend too much time to solve a few updates. And the fast hybrid is okay too, interesting too, because the combination of the serial plus the Q propagation, but we found that the number of first interactions by scanning, the number of initial scans is an open problem. We can speed up very much the solution if you find a good estimation for the number of first scan. And practically, you may say that will never be one scan. Usually 2, 3, up to 2 or 3, there will result in a reduction of the global time. So the best result is maybe subject for machine learning to try to treat, because it's not easy. The processing time depends on the contents of the image, how is the shape is, and the interactions between the shapes, and then it's very, very hard to find some good heuristic to solve that. So in terms of research subjects, machine learning for image reconstruction is quite promising. In fact, image reconstruction is a very large topic. People from the biomedical research, you can think you have several devices that may acquire images from the body, and those devices may introduce different kind of noise or maybe some distortions on the image, and you need techniques to rebuild the correct image. So morphological manipulation is one option. You can find a lot of machine learning and deep learning, for instance, applied to image reconstruction. So it's a very large field with a lot of interest for the medical community. And other things, for instance, is curious because you do the acceleration FPGA and you compare with, for instance, the image reconstruction done in a PC, for instance, in MATLAB, you can call a function IM reconstruct, and it's really very, very fast, very, very fast. It's difficult to beat that with the time of a MATLAB reconstruction with our FPGA. So I saw some publication where the guys must increase a lot of the size of the structural element. So in those cases where the structural element is big enough, so the reconfigurable architecture starts to be faster than the desktop computer. So that's because they say it's because you can do some runtime optimizations. That's the thing that you usually don't do in hardware. So maybe runtime optimization could be combined with the dynamic reconfigurable architectures to find better solutions for those applications. And of course, there is a lot of experiments. So I'm working with instruction set with reconfigurable instruction set processor, so you can try to customize the instruction set of the processor for those operations, like to build like a morphological processor, for instance. So there is a lot of room for improvement and research in this area. Well, that's all. I got more or less on time. I'm happy to finish more or less on time, and I am available for questions and discussion.
Thank you, Jacob. Very nice presentation. Very nice talk. The subject is really very important for our community in CASS, and you presented a very interesting discussion about the context of the problem and also some solutions targeting hardware. This is very, very important. We don't have questions for the audience. Please, guys, do your questions at the chat. But I have some questions here. You talk about the issue related to memory. Do you have some alternative to try to solve this problem? Since considering your presentation, maybe the memory is the main problem to allow the support of
Yes.
very high resolution images.
Yeah, the memory is really a big problem, but I think that if you have a specialized architecture that will have a large bandwidth, even having a large bandwidth, in the case of those operations, you need a bit of internal memory to store or at least part of the images. So there is some technique of partial buffering that you could try to use, and if you have enough bandwidth, maybe if you go for the FPGA cloud, for instance, where you have larger FPGAs and much more memory, and you have a good bandwidth to communicate with memory, you could try to that's my idea. Maybe you could try to beat the competition. So they say that I saw some good results with many cores and some GPUs too. But with large FPGAs with a good bandwidth, and of course, you must think about how to do the buffering. Buffering is crucial here because you must store some intermediate, some internal partial results inside your FPGA, and maybe if you have enough speed, you can swap this with external memory, and then you could really go to a high level of performance.
Okay. Other simple question here. Why do you decide to use support vector machines instead of the other methods?
That's our very well in the university. It happens that there was in the group we were working with some colleagues in the mechatronic lab. So there was one PhD student that was working on support vector machines, and then he started cooperating with us. But there is no specific reason to use specifically support vector machines. It was that we have somebody working on that, and then we asked him to discuss. He got interested by this problem because it's very hard. So even to know which parameters you should monitor to do the guessing is not easy. So only for that reason. So not that support vector machines are better suited for this kind of problem. So we should try to. There are other guys work with in the same lab. Of course, I must say that other guys work with particle optimization. So swarm optimization, so on. They tried that too, so that seems that was not that good as support vector machine, but we haven't tried, for instance, deep learning or neural networks and so on. So it's open, it's still open.
Okay, very nice. Questions? Professor Altamiro Suzin said that very interesting approach. Thank you for the presentation. I have two questions. One, in the case image partitioning, what is the size of the blocks? Do they depend on the kind of imaging?
Good question. In fact, there was one experiment that I didn't mention because did not provide good results because, well, of course, the size of the images, the sub-blocks will depend on the size of our FPGA. So in our case, we could work with, I think it was 1,000, each block with 1,024 pixels by side. And another thing that we tried to experiment was the shape of it. Since you have to reprocess the borders, we are trying to see, it's better to have a block with 1,024 by 1,024, or it's better to have 128 by the you have 24, so 4. Yeah, so you make the same amount of pixels if you put the same amount of pixel, but in a different shape, more rectangular shape. And in fact, what happened is that we found that the square solution, dividing the image in squares was the best solution. And it was not what I thought. I thought that if you have, for instance, a large a strip like that, a small 8 but very large, will reduce the number of reprocessing steps, but it was not like that. So I don't know why. But so the size of the image depends on the platform. So of course, on the best platform, we could use 1024, 1024. Remember, we must have the marker and the mask, so both images inside. And of course, so we do the processing, updating the marker based on the mask is just for consulting, but in this case, we need to store 2 images inside FPGA.
Okay, another question here from Professor Reis, I believe. Wanting to save power as more and more big issue, one option is to use hardware accelerators. What about hardware accelerator for morphological image processing? I believe here he's talking about hardware in ASIC, completely dedicated hardware, I believe. I don't know.
No, yeah, it's okay. That's a good question. We do have, if you may find in the literature, they do some morphological coprocessors. So the difference is that the focus is since you have a coprocessor, the idea is to be more energy efficient. They implement all the images, all the basic operations. So in that case, frequently you don't find a specific implementation for the morphological reconstruction. So you still can do morphological reconstruction because you can do, for instance, those pipelines of morphological operators. So you can apply very fast a lot of structural elements to do dilation and erosion. But still, if you do morphological reconstruction with those operations, it takes more time. But it's an approach that we have already some work in. I saw some publications on the literature. And of course, that goes well to put, you migrate those functions to an FPGA. If you have like an Intel with Stratix and x86 processor, you can migrate implementations for this coprocessor on implement on the FPGA. And of course, you are going to save power. There is specifically, I saw one paper that was analyzing the performance of GPU, many cores, and FPGAs, and of course, FPGA was the most efficient in terms of power consumption or energy consumption.
Perfect. Another question from Professor Altamiro Suzin. Hello, Suzin. How are you? If you have a stream of images, do you think you can build some kind of pipeline? What will be the time spent to transfer the images related to the time to process them?
That's the good question. Yeah, that's a good question. Suzy, yeah, for the basic operation, yeah, everybody does that. So you have a pipeline, and the pipeline means that you can apply several. You mean if you're scanning the image, you can apply a pipeline that you start scanning with morphological structural element, and then apply another one, and you can do that. And even if you have a lot of hardware, you can do different, like a data flow. You can put a dilation, erosion in different modules. You can. It's quite feasible to have the image flowing, a stream of pixels flowing through those operators. For morphological, but in our case, we should have an implementation where we do use the partitioning on the SOC FPGA. So the image must go from the memory of the ARM processor, so transfer to the FPGA, and that takes time and limits exactly the relationship. But for instance, I remember that in this case on the SOC kit, just to start. You can use burst transactions, and burst transaction can send a lot of pixels. But just to start the burst transaction, I remember that we must wait several cycles, and then we start the burst. And the burst was limited. Depends on the FPGA. Was limited by the size. I guess was, I don't remember what's the bandwidth, but I think it was 64 or 100. 64 bits, for instance, we can send in each transaction. And so I was talking before, so just the pipeline like that is easy. I think it's easy to do for the basic operation. For those operations to make several iterations, that's more complex. So, but for opening, closing, for dilation, erosion, and there's a lot of other operations that you can obtain based on those. You can use a pipeline very straightforward.
Okay, thank you, Jacobi. Guys, you have some additional question? You can wait a little bit more for additional questions. Altamiro Suzin tells, thank you, nice to see you.
Nice to see you, Suzin. Nice to talk to you. Very nice. I was telling, it's a pity that I was talking with Ricardo and Luciano, and it's a pity that we cannot meet presentially. Hope that we're going to end soon this restriction.
Sure. But it's very nice to see you here. It's very nice to share with you our questions, and we thank you very much for presentation. The topic is very interesting, and it's very important. We have some references in Brazil to talk about this very important research issue. And then now the guys in Brazil and the rest of the world, as you know, Professor Jacobi has a very, very interesting work in this subject. Okay,
thank you very much,
Jacobi. Thank you very much, everybody.